You take microcanonical, canonical, and grand canonical. So you ask, what is a quantum ensemble? A classical ensemble is a collection of systems, the same copy of the system. What is it in quantum mechanics? We have to first understand that. We're talking about a system which is immersed in an environment. The system may be, say, a test tube of your gas, and on is the rest of the world. So the Hamiltonian of the system H, we will get H of the system plus H of the environment plus interaction. Let us suppose that the system is a H system. We use the describe it on, say, phi n of x and t is equal to En of phi n of xt. These are the eigenstates of the Hamiltonian, and En are the eigenvalues of the energy. And usually we assume that phi n forms a complete set of wave functions. Of course, x is a summary of all the coordinates. It could be n particles. So in general, no, there's no t. This is eigenstate, stationary value. In general, phi of x and t can be expanded as a linear superposition of eigenstates of the Hamiltonian or any other complete set, but this community uses. So just say equal to Cn of phi n of x. And this depends on t, of course. But more important, it also depends on the external coordinates x. Here's the environment. And these are different eigenstates of the system. The probability of finding a system in state n is the magnitude Cn of t and x quantity squared is the probability of finding system in phi n. So it depends on the time, but it depends on x. So x is a very complicated thing. So if x changes a little bit, a truck goes by, this changes. And if you notice exactly, this is just one, this is a pure state, this is a pure state, this is a pure state. It is a coherent superposition. So let me emphasize, a pure state is equal to a coherent superposition of eigenstates. Coherent means that all the C's are well defined, definite numbers. Then no matter how complicated C is, it's just one state, one pure state. However, an ensemble is an incoherent superposition. Incoherent superposition. That is, the Cn's have random relative phase. So there's no interference. There's no quantum interference between different eigenstates in this case. The CMs have random relative phase. Can you read this random relative phase? And I think you can understand this very well. If Cn depends on x, and x is the variable of the external world, so it's very complicated. You change x a little bit, the phase changes. So if you take two different C's, the phases are random, because if a truck goes by, the phase changes. Therefore, there's no superposition, there's no interference between the two systems. The system dephases. In that case, you can think of each phi n as a copy of the system that have nothing to do with each other, and that's our ensemble. So that a quantum ensemble is an incoherent superposition. It consists of copies of the system, eigenstates that have random phases with respect to each other. And the main difference between quantum mechanics and quantum mechanics is the existence of the quantum phase. So that when you address the quantum ensemble, the question is, what do you do with the quantum phase? The answer is, in a quantum ensemble, the relative phases between different copies of the system are random. That means there's no interference. More specifically, the average value of a quantity, the average, say, O, is equal to psi, O psi. You take the expectation value, and you average over x, over the external variables x. You average over the external world, and the result is that the interference terms averages out. That is, this is equal to summation m and n Cm star of x and t Cn of x and t times phi m O phi n. And you average over this. Average over x. Once you perform the average, it is reasonable to assume that the result is diagonal. That is, there's no interference, times Cn, some Cn of t, the x being averaged out. And that CNT gives you the probability. And this gives you an ensemble. This assumption gives you an ensemble. This no interference assumption gives you an ensemble. And therefore, the average value of any quantity is equal to summation Cn squared phi n O phi n. You take a diagonal element. And of course, we assume that summation Cn squared is equal to 1 because it's a complete set. So, and this defines what is meant by quantum ensemble. You take a set of eigenstates, usually of that of the Hamiltonian, and you say that when you average any quantity, you just take the expectation value of the Hamiltonian and weight it by different coefficients without interference. And the ensemble is defined by the choice of these numbers Cn. I want to emphasize that the difference between a pure state and a coherent state, right? Take an example. Suppose I have a spin state. Spin up and spin down. If I add these two states, so psi of spin up plus psi of spin down. If I just add these two states, I still get one state. And that state is psi with spin pointing in some other direction. You just rotate the spin direction. You just get one state. However, if you take psi up, alpha plus beta, psi down, and alpha and beta have relative random phase, then you have incoherence. Then you have a situation in which the system is half the time with spinning and spinning, half the time with spin down. You have an ensemble. This is an ensemble, this is a pure state. In a scattering experiment, for example, if you take a target, scattering. If the incoming beam, say if we get an electron beam coming in, the polarization is either this way or this way. If you superimpose these in a coherent way, you just get a beam with a spin pointing in some other direction. But if you take an incoherent superposition, then you get a certain this is called an unpolarized beam, which is an ensemble. I don't know if that makes it clearer, but to those who are familiar with scattering, that's the example. An unpolarized beam is characterized by an ensemble, but a polarized beam is a pure state. Now, since it's a pure state, you never mention the wave function. You just mention the coefficient Cm. There must be a way to formulate this. So we never mention a wave function. And yes, then that's called a density matrix. The density matrix Rho Mn replaces the classical distribution function for ensembles. It's defined in the following way. In terms of a particular basis. For example, eigenstates of Hamiltonian, which is usually what we use. And we define this matrix as Rho Mn is equal to delta Mn times the coefficient Cn squared. Cn squared is the weight of the nth eigenstate in the ensemble. And this density operator rho is such that if you take rho between m and n, you get rho Mn. And so you can write rho as m rho Mn n sum over m and n. And the thermodynamic average is then the trace of rho times O. Now the trace is independent of representation. You can calculate any representation, you get the same answer. Therefore, you can calculate this trace in this representation. So it's equal to summation of n rho O n sum over n, which is equal to sum over n rho m O n and m. And since this is equal to delta Nm times Cn squared, you get sum over n of Cn squared of n O n, which is what we have before. So then, by defining a density matrix or density operator and using this formula, that's a very convenient way of defining the quantum ensemble. I forgot what this divided by the trace of rho. So in this case, it will be the whole thing divided by, this was divided by summation Cn squared. Since we have discussed the microcanonical ensemble, canonical and grand canonical in classical statistical mechanics, now it's nice to ask what are the rho NMs corresponding to each of those ensembles. And the translation is very direct. So for the microcanonical ensemble, you just take rho Mn is equal to delta Mn times Cn squared, of course, and Cn squared is equal to 1 if the energy lies within E plus delta and E, where epsilon is the nth eigenvalue and 0 otherwise. And this means that rho, the operator, is equal to summation over n of this combination. The n is such that epsilon n lies between E plus delta and E. And again, once you have this, then gamma E, this is a trace of rho. And the entropy is K log gamma E. This then gives you the complete thermodynamics. Now, if we go to the canonical ensemble, then rho Mn is delta Mn, that is this diagonal in the energy representation, times e to the minus beta epsilon m, where epsilon is the nth eigenvalue of the Hamiltonian. And this means that rho, the operator, is just equal to e to the minus beta h as an operator identity. And this means that Qn of V and T is equal to the trace of e to the minus beta h. Now that's a very beautiful formula. It connects with the thermodynamics immediately, because that's equal to e to the minus beta times the Helmholtz free energy. You see that there are no extra constants. And T comes in because beta is 1 over kT, and the trace, and V comes in because the trace traces over all wave functions contained in the box of volume V. And there are no dimension parameters to fix and so on. Planck's constant is inherent in here. So that's a very nice formula. And the grand canonical ensemble is the same. You just take the grand partition function to be z to the n times Qn sum over n, just like before. So I don't have to particularly mention the grand canonical ensemble. A very important thing is, how do we do computations? How do we calculate things in the quantum case? We'll illustrate this with ideal gas. In a microcanonical ensemble. You take the ideal gas, you put the ideal gas in a box. Then the energy eigen, then the particle state is labeled by k, a wave vector. So that epsilon k is h bar squared, k squared over 2m. And k is a wave vector in that the wave function of a single particle psi of x and t is equal to some constant times e to the I k dot x. And we put this in a box whose length on the x-axis is L, then you have to specify boundary conditions at the boundary. For example, you might choose the one has a vanish here, but more conveniently, we choose periodic boundary conditions. Which means that whatever the wave function, whatever value here, it has to repeat here. It could do this and then you have to come back to here. And that means that k is quantized. K has to be 2 pi over L times n, where n is a vector, components of n are 0, plus or minus 1, plus or minus 2, and so forth. And this makes the spectrum discrete. And it becomes a continuum when L goes to infinity in the continuum limit. And this makes it convenient for counting purposes. This means the spectrum of a single particle becomes a discrete spectrum. But the spacing is of order 1 over L, so it goes to 0. L is macroscopic. So when we do the counting, it is connected, cut this up into cells. You notice 1, 2, 3, and so forth. Cells. And the degeneracy in each cell is G1, G2, and so forth. That's the number of levels in the cell. And the energy is epsilon 1, epsilon 2, and so forth. And you can specify the state of the system by saying how many particles are there in each cell. These are occupation numbers. This is N1, N2, and so forth. These are occupation numbers. And we have to assume that these are very large because we're doing statistics. So we don't want to, we are not interested in single levels. We're interested in the groups of very large number of levels. So the G's are very large. And of course, in the limit when L goes to infinity, any finite assignment of G will make it contain an infinite number of levels. A state of the n particle system is labeled by set of occupation numbers. I denote it this way. And this is shorthand for N1, N2, and so forth. And in the microcanonical ensemble, I want to choose the states in such a way that the sum of Ni is a fixed number n, and the sum of Ni, epsilon I, is equal to E. And these are the constraints that define the microcanonical ensemble. Therefore, now the task is to compute this volume gamma E given these conditions. So what is gamma E? It is that given n and E, how many states are there that satisfy these conditions? So we have to count. It is in this counting process that we have statistics. Since a state is this corresponds to a set of occupation numbers, gamma E is just the number of states satisfying those conditions. So let W of n be the number of states corresponding to the given set of occupation numbers. Like, for example, I said in cell 1 I put 2 particles. In cell 2 I put 10 particles. In cell 3 I put 7 particles. How many states does this correspond to? And that's Wn. And gamma E just equal to sum of Wn over all n. So now let us consider what you do. The particles are identical in quantum mechanics. That means interchange of 2 particles does not lead to a new state. For example, here's cell 1, here's cell 2. Suppose I put the particles here like this. If I interchange these 2 particles, I do not get a new state because the particles are identical. You cannot tell the difference. Whereas classically you can. Here you cannot. So interchange of these 2 has no effect. Therefore, you forget about exchanging particles in different cells because you exchange them, there's no difference. So how do you count states? It's in each cell. You count how many states are in each cell, then you sum over all possibilities. It is in each cell. Say cell 1. Cell 1 has GI levels, and you put Ni particles in the GI levels. How many different ways you can put it in? You have different patterns. It's a number of patterns that give you the number of states. You could do it this way, or you could put it this way elsewhere. It's the pattern that matters. So this is the crux of the matter. In order to emphasize this, let us compare what we did with classical statistics. What we did classically. How did we count? Here are these n cells. And we have n particles. We sprinkle this n particle into these n cells. First way that they're n factorial combination. We have n factorial. And this comes from the fact that if you interchange two particles, I get a new state. So each permutation gives me a new state. That's where this n factorial comes from. And then I divide by n1 factorial, n2 factorial, because in each, when I interchange this sum doesn't change, so I have to divide it out. That's what I get, right? And then we say that you divide this out by correct Boltzmann counting. Just leave it out. That's inconsistent. First you say that they're distinguishable, so you say n factorial. Then later you say, oh, this is not distinguished, you kick it out. It's not consistent. So classically, the correct Boltzmann counting is a mathematical recipe that has no explanation. Whereas now, we really consider particles, regard particles as indistinguishable. So the only thing that makes it different is the pattern of occupation in a single cell. So we will not count patterns. There are two different kinds of statistics. There's Bose statistics and there's Fermi statistics. In terms of what we're doing, what this means is in both each ni can assume 0, 1, 2, up to infinity. Whereas in Fermi, this is only 0, 1, that's it. That's the Pauli exclusion principle. No two particles can occupy the same state. Whereas in Bose, you admit all. And in terms of a more fundamental property, Bose means that the wave function psi n x1 up to xn is symmetric whereas in this case it's anti-symmetric, which means that if you interchange any two, the wave function does not change. Where if you interchange any two, the wave function changes, the wave function changes sign when you. That's the medium statistic. Now if you take both symmetric and anisotropy wave function, you take the whole group, then you get both symmetric and anisotropy wave functions. That is not classical. Classical is this plus a whole bigger group of no symmetry at all. That's a much big larger group. When you take that, you get classical statistical mechanics. So these are very special. And when you add them to, it's still amongst a very small set of all possible wave functions. The great majority are wave functions with no symmetry at all. You interchange 1 and 2, it's just a different wave function. So now let's count. So for Bose, you take one cell. This is a cell. And it contains GI subcells. And it contains Ni particles. Question, how many different patterns are there to distribute Ni particles into GI subcells? And the answer is you can do it this way. You can put the particles in, these Ni particles, and they are GI minus 1 partitions. If I interchange the partitions, if I interchange the particle and the partitions, for example, if I interchange these two, I will get a new pattern. And then the number of patterns is Wni is equal to Ni plus GI minus 1. These are the things in here, particles plus partitions. I permute them. And then I said that if you permute just the particles, it makes no difference. And therefore, divide by ni factorial. And if you permute just the partition, it makes no difference. So divide by gi minus 1 factorial. So this is both. Now that's a very clever trick. In fact, it took people a long time to discover that. Now Fermi. For Fermi, let me use the same picture here. For Fermi, you can have two. Each cell has at most one. The other was empty. And therefore, the number of patterns is the number of ways to choose ni things out of gi things, out of gi minus 1 thing, out of gi things. That is, the pattern is determined by which of the cells you choose to be occupied. And therefore, Wni is equal to number of ways to choose the Ni occupied subcells, because each cell can only accommodate at most one particle, or equal to the number of ways to choose Ni things from gi things. How do you choose Ni from gi things? Or equal to gi factorial divided by Ni factorial divided by gi minus Ni factorial. And this gives us the answer. And then the rest is just working it out, which is now have to sum this over n and compute gamma n. Now to compute gamma n. So I hope that you realize that there's two different kinds of statistics, so-called. Gives you very different ways of counting. That's why it's called statistics. Whereas the classical case is no counting at all. You count and then you change your mind by dividing by n factorial. The classical case is sometimes called Boltzmann Statistics. So, okay, entropy S over K is equal to log gamma E, which is equal to log of summation over n of Wn. And again, we anticipate that there is very little fluctuation, so we say this is roughly equal to log of Wn bar, where n bar maximizes Wn. And Wn is already given, so we just calculate. Let's look at the Bose case. Log Wn is equal to, I just take the, I already erased it, but you have to. I just take the logarithm of what we found and use Stirling's approximation. So you get Ni plus Gi minus 1 times log of ni plus gi minus 1 minus ni plus gi minus 1. That's from the first term. And then you have a term plus minus ni log ni plus ni. And then you have a term minus gi minus 1 log of gi minus 1 minus gi plus gi minus 1. And the last column cancels. These cancel, leaving you with just this. And if you add those terms up and use a little algebra, do a little algebra, you get a final answer that looks like this. You get log of ni plus gi minus 1 over ni, sum over I. This is equal to S over K. This is what you get. And now you must vary ni to produce a maximum of this term. So, but when you vary it, the ni's are subject to constraints. So now you have to add Lagrange multipliers. That is, you must take variation of S over K. Minus alpha n minus beta E is equal to 0. That is to say, delta of ni, delta of log ni plus gi minus 1 divided by ni minus alpha. There's a sum over ni. Delta ni minus beta ni epsilon I is equal to 0. Now you can vary this. You could just vary the ni independently because of these Lagrange multipliers now. So it's a matter of algebra, and you get log ni plus gi minus 1 divided by ni minus alpha minus beta epsilon I is equal to 0, which finally gives you ni is equal to gi minus 1 divided by e to the alpha plus beta epsilon I minus 1. And you can neglect this because gi is much greater than 1. And so you get a Bose distribution. Ni is equal to gi divided by e to the alpha plus beta epsilon I minus 1. This is Bose distribution. The alpha and betas are determined by applying the constraints. And the constraints are summation Ni is equal to n. This means summation I gi 1 over e to the alpha minus beta epsilon I minus 1 is equal to n. Now summation times gi will, as the volume goes to infinity, will go over to an integral. That integral is L over 2 pi times integral dkx 3 times. So it's L over q dkx, dky, dkz. Oh. This L over 2 pi cube comes from the periodic boundary condition way of counting. And this is just equal to v over integral d3k over 2 pi cube. It's always coming. The dk always goes with a 2 pi, quantum mechanics. And therefore, the condition here is integral of d3k of 2 pi cube 1 over e to the eta minus beta h bar squared k squared over 2m minus 1. That must be equal to n over v. So that determines one of the constants. The other is using the energy. And as you know, the answer is beta is 1 over kd, just like before. And alpha is just equal to mu over kt. Chemical potential. And that's the Bose-Einstein distribution. And we do the same thing for Fermi. If you repeat the same thing for Fermi, you will find that Ni is equal to gi divided by e to the alpha plus beta epsilon I plus 1. The only difference is sign. And this gives you the famous Bose and Fermi distributions. Now, this alpha, beta is the temperature. This alpha is a chemical potential. It has to be determined in terms of the density from this radiation. So it's not trivial. It's not clear how alpha behaves. You have to solve this. So that if you say that, so alpha is a function of the temperature also. So if you ask how does it behave at high temperatures, you have to know how alpha behaves. So you have to work it out. I would like, however, to calculate the grand partition function for these two cases. That's a very instructive calculation. And also, once I do that, I have the equation of state. Do I have time? Well, maybe I'll do it next time.